there are three important properties of relations that we're going to talk about, and that's what section 11.2 is on. So those properties are called reflexive, symmetric, and transitive properties. And we're going to go through each of them here. So a relation R is reflexive if x are x for every a and x. So what does that mean, right? So anytime I have some sort of a and x, for every single one of those, it has to be related to itself. So let's look at some examples as we go here. We can look at, say, the equals relation, and maybe we'll also think about less than or equal to and not equals. So is it true that for every single element, let's let our set A be the integers. So is it true that any single x is equal to x? Well, yes, everything is equal to itself. So that equals relationship is reflexive. Is it true that for all x, x is less than or equal to itself? Well, yes, that is true. So less than or equal to is reflexive. But if we consider for all x, x is not equal to itself, that one's not true. Right? No x is actually equal to itself, so that's not a reflexive transformation. Now moving on, we have symmetric. So a relation is symmetric if whenever x and y are related, then y is related to x. So you can basically switch the order around. Right? So if you have a relation in one order, then you can switch it around and you get the same order. So let's think about what that means for each of our properties we have down here. So is equal symmetric? That would say if x equals y, then y equals x. That makes sense. That one's going to be true. For less than, it says if x is less than or equal to y, then y is less than or equal to x. That's not true. Just because x is less than y, we don't get y is less than x. And then the last one says if x is not equal to y, then y is not equal to x. That's true, right? If they're not equal, then they're not equal. And that has to be true for everything in the set. Right? It's not just for some x and y, but for all x and y. Okay, finally we have the transitive property. The transitive property says that two things are transitive if whenever x is related to y and y is related to some other z, then x is also related to z. Right? So for all x, y, and z, if x are y and y are z, then x are z. So what transitivity says, right, if x is equal to y and y is equal to z, we sort of use this all the time without really thinking about it, then x is equal to z, right? We know that one's true. If x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. We've also seen that that is true. And a lot of times people would, again, use these without really thinking. And the last one would say that if x is not equal to y and y is not equal to z, then x is not equal to z for all x, y, and z. So if you think about that, right, maybe x could be something like 1, y could be something like 2, but then z could be 1 again. Then I have x not equal to y and y not equal to z, but I'm going to contradict the conclusion. I'm going to have that x is equal to z. So that one I have a counterexample for, so that's not a transitive relation. So what we want to do is we want to be able to identify which relations are going to be reflexive, which ones are symmetric, which ones are transitive. And then next we're going to focus on the ones that are reflexive, symmetric, and transitive. these are our equivalence relations. So we'll see that those have a lot of special properties that we care about. All right, to check your understanding of these definitions of reflexive, symmetric, and transitive, I want you to determine if each of the following relations, the strictly less than relation, the divides relation, and the does not divide relation, are reflexive, symmetric, and transitive, and we'll talk about that in class. Let's look at one more example here. So let's say we have A as the set A, B, C, D, and R is equal to this relation given by BB, BC, CD, CC, DD, BD, DB, CD, and DC. Let me go ahead and just update that one quick second. I'm going to change that guy to a B. Okay, so is this reflexive? So remember, for it to be reflexive, for every element in the original set, that element must be related to itself, right? Which means that everything must be paired with itself and exist in the relation. So I need to have D paired with itself, and C paired with itself, and B paired with itself, but also A paired with itself. And I notice that AA is not in R. So it's not the case that for every element in A, it's related to itself. So R is not reflexive. Okay, for symmetric, we need to check if X, R, Y, so if X, Y is in the relation, then YX is in the relation. So I could write that as YRX. I could also say if XY is in R, then YX is in R. So here what I need to check is that for every element in my relation, the switch, when I change the order, it's also in there. So since BB is in here, then, well, BB just switches to itself, so that's fine. BC is in here, so then CB has to be in here. So that's good, those ones pair up. CC switches with itself, so that's fine. Same with DD. BD, that switches over to DB, those are both in there. And CD switches to DC, so those are both in there. So it's true, for everything that's in there, its switcheroo is also in there. Thus, we can conclude that this relationship R is symmetric. Finally, we want to check transitivity. So that says if you can kind of pair things up. So if X is related to Y and Y is related to some Z, then you get that X is related to Z. So if I can kind of chain things together, then when I put them together, I can get that. So what do I mean by that? So let's see what I can chain. So if I start with B, D, because that's in my set, I can chain that with something else that starts with D. So I see that I have a, say, DC. And since these two match, if it was transitive, then I must have BC in there, which I see that I do. This one's harder to check because there's just so many things to go on and so many things to look at. So sometimes if we draw out this graph relationship, which we talked about, then we can be able to visualize this better. So let's go ahead and graph this guy out. So I'm going to just plug my letters in here. I know that B is related to B. B is related to C. And C is related to B. I know that C is related to C. D is related to D. B is related to D. D is related to B. And C is related to D. And D is related to C. So I get all of these arrows here. These little loop-de-loop arrows, the ones where it's connecting back to itself, that's what we need for reflexivity, right? So each of these had that loop-de-loop, except for A, so there's no loop here. So that's going to tell us that A is not reflexive. Well, that A is not related to itself, and therefore the whole relation is not reflexive. So we can see that just by looking at this graph. For symmetry, whenever we have an arrow going one way, we should have the arrow going back the other way as well. So these three things together, we can see anytime you go one way, you go back the other way. So we can see that symmetry there. And now for transitivity, it's harder even to see here. Well, not harder, but it's still hard to see, right? Anytime I go from one place to the next, I should be able to go there directly. So if there's any path from B to D, I should be able to go directly from B to D. But what I can see is that A doesn't connect to anything. So there's not going to be any breaking of transitivity there. And B can get either to C or D directly. So even if I go B to D and D to C, I can get B to C because I have that direct arrow. So because everything else is connected to everything else, including in the loops, right? So we have to be careful because we have like B to D and then D to B. So I get B to B. So I actually have to have that reflexivity. So anytime I have two that match up, I get that following relationship. So this is transitive. So that's definitely the hardest one to check. So last, here's a question for you to think about, and we'll discuss this in class. So if you have a natural number n, we want to show that the relation R on Z, given by A, B is an R if A is congruent to B mod n. So that's one that you already thought about a little bit. We want to show that that's reflexive, symmetric, and transitive. So let me correctly spell symmetric here. So I encourage you to go through and try to think about how you would prove those. Right? Each of them is going to be some sort of proof, right? Reflexive is a for all proof. Symmetric and transitive are going to be if-then conditional proofs. So we'll work through those proofs in class, but I encourage you to give them a shot beforehand just to see if you can figure out how those work.